Hey guys, this is the last part of chapter 12, 18th century or the 1700s, and then going into the early part of the 19th century. PowerPoint is on Brightspace and starting with slide 10, I believe. So I want to talk about a few relatively minor people briefly, and then two heavy hitters, and then talk just a little bit about measurement. First of all, D'Alembert, one of the founders of partial differential equations. So imagine that you have a guitar string hooked at both ends and you plucked the string and you talk about the motion of one of its molecules over time. So it vibrates back and forth. Let's let t be time and x is the distance from one end, say one of the frets, to the particle, the molecule that you're talking about. And u is the distance that this particle is vibrating back and forth. And we'd like to know the motion of this molecule if I tell you what time we're at and how far along the string we are. So D'Alembert came up with the so-called wave equation, very important in mathematical physics, not so important here. C is the speed of light, by the way. But the important idea is the ability to use calculus like this to describe fundamental properties of mathematical physics. So not only do guitar strings vibrate this way, but so do light waves and sound waves and any other kind of wave that we really think of. Not only did D'Alembert come up with the equation, he was able to solve it and found that every solution looks something like this. So a rather vague description, but the important part is that this describes traveling waves. If you've ever looked at a slow motion of a guitar string or a piano string, you see these, these so-called standing waves and traveling back and forth on the string. And that's what this solution predicts, this mathematical solution predicts. Again, today, most equations of mathematical physics are partial differential equations. So this wave equation and things like it are how we describe our world. Next person, Agnesi, was a woman in the late 1700s. Most of the mathematicians we've talked about have been child prodigies. They were very good at things from a very early age. But Agnesi was an extreme child prodigy. She wrote her first publication at age 9. It wasn't math, but still the idea of a 9-year-old writing things for a journal is astounding. She got her education in part by listening to guests of her father who would come in from all over Europe. And since she herself spoke 6 or 7 different languages, she could always eavesdrop and well, more than eavesdrop, talk with them and find out what's going on. Very interested in math and science from a young age. She then became the first female university math professor that we have record of, at least in modern times when professors had the same kinds of jobs as they typically do today. And she is one of the early proponents of good math education. So this new calculus material is out, but it's hard for people to understand, and so we need someone to write good textbooks. Agnesi wrote a 2-volume textbook about calculus and other math. And first of all, she wrote it in Italian rather than Latin, so that more people had a chance to understand it. And then she was very, very conscious and very, very good at writing for people without much experience. So this is who you would want to learn from, someone who was writing for people with the goal of teaching rather than just of documenting. Oddly enough, one of the things that her name is most commonly associated with had to do with the fact that she was studying curves like this, which are, I believe, equations describing curves describing how wind blows into the sails of a boat. And through a mistranslation that she did in English, it became translated as witch instead of curve. So her work, and she is now known as the witch of this curve is known as a witch of Agnesi, even though she herself was actually a very nice person and a humanitarian. Let's switch to Lagrange, who was one of the two heavy hitters of this time period. By the way, most of the top mathematicians of the late 1700s were in France and Italy. And Lagrange was one of the first people to throw up some red flags and say, hey, we better be careful about what we're doing with this calculus. It's wildly successful at explaining physics, for example, but some things could go wrong. So for example, if we look at this equation, the sum 1 minus 1 plus 1 minus 1 plus 1 minus 1, and ask, what does this add to? One thing we could do is group like this. So here's 0 plus 0 plus 0. So obviously the sum is 0. But if we save out the first one, then it's 1 plus, and negative 1 plus 1 is 0, negative 1 plus 1 is 0, negative 1 plus 1. So this adds to 1 plus 0 plus 0, and of course the sum is 1. Well, which is it? Does this thing add to 0? Does it add to 1? Does it add to something else? So now we would say that, because we know about limits, we would say that this series does not converge at all. And so to ask about its sum is kind of a dumb question. But people back then didn't know it. And sooner or later, people were going to start coming up with erroneous results because of not paying attention to things like this. Lagrange knew this. And so he wrote what we would call today the first real analysis textbook. In it, he tried to give greater rigor to the foundations of calculus and analysis in general. He himself was mostly unsuccessful in this, but at least he started the conversation, the idea. And then people later in the 1800s picked up on this and did it successfully. Lagrange was very careful in all of his writing. He wrote deliberately and proved everything jot and tittle, and wrote everything very rigorously and tried to make it understandable. One of the other things he did was develop the calculus of variations. The Bernoulli brothers had started this, but Lagrange took it a lot farther. A couple of optimization problems here. In Calc 1, we talk about maximizing a function. So here's a polynomial. Say we want to know for which x between negative 5 and plus 5 does this function have a maximum. Maybe x equals 3 or x equals negative 1 or whatever. Well, in calculus of variations, you talk about functions of functions. So here, u can be any smooth function on the interval 0 to 1. And when I take that and plug that into this definite integral, each time I plug in a different function, I get out a different value. So if I take u equals, say, sine of x, then I get something for this integral. If I take u equals e to the x, I get something else for this integral. And the question is, which function should I plug in to give the largest value of the integral? That's a good calculus of variations problem, and Lagrange was very successful at solving things like that. Some other things that he did in Calc 3, if you've taken that class, and remember there's something called Lagrange multipliers. So if you're trying to do an optimization problem in multivariate calculus with a constraint on it, then often you write down an equation f equals lambda times g, if you remember that, and this lambda is the so-called Lagrange multiplier. This method is due to Lagrange. Maybe the most important thing that Lagrange did was come up with the so-called Lagrange equations, or just Lagrangian. So Newton had developed laws of motion that very successfully explained how objects moved. For example, a stone is rolling down a mountainside or something. But Newton's methods were written in rectangular coordinates, x, y, z coordinates. And the stone was rolling down the mountain long before, or stones rolled down mountains long before Newton came along. And so why should how we describe a stone be dependent on how we choose to describe our coordinates, our space coordinates? I mean, people were also now using polar coordinates. So what if I want to describe the motion of the stone in polar coordinates instead of rectangular coordinates? And there are also spherical coordinates and so on. Lagrange said, wait, let's back up, and we can describe motion in a way that's coordinate free. So we can talk about the motion of this object without committing ourselves to working in a particular coordinate system. A very powerful idea. And then a couple of other things that he did from different areas of math. Here's 3, and here's how it can be written as the sum of the squares of 4 integers. Here's 31 and how it can be written, 310 and how it can be written. And if you pick other integers, 257 and so on, it turns out you can do this. If you're clever enough and work hard enough, you can write it as the sum of the squares of 4 integers. Lagrange proved that, in fact, you can always do this for any positive integer. And I won't go here, but here's an interesting website where you can go and the app asks you to enter any positive integer of reasonable size, maybe 15, 20, 30 digits, and it will come up with a way of writing it as the sum of 4 squares. The proof was difficult, and Lagrange showed that he was a brilliant mathematician to be able to prove that you can always do that. Some of you have had abstract algebra, some of you haven't. If you have, you remember there's a group, something called a group, and something called a subgroup. For the rest of you, an example of a group are the integers 0 through 5 under mod 6 addition. That's a group. And then if we take the subset 0 to 4 and still use mod 6 addition, this is a so-called subgroup. And Lagrange says the subgroup is of size 3, the big group is of size 6, and hey, 3 divides 6. That always happens. The size of any subgroup divides the size of the group. The other big hitter is Laplace. So most of these mathematicians were from France or Italy, sometimes Germany. Laplace, like Lagrange, was also interested in mathematical physics. And so some of the things that he did in partial differential equations led to the way we describe electrical potential or the transmission of heat. So for example, for the transmission of heat, you put a cooking pan on a fire, and how does the metal warm up? Or for potential, you rub a balloon, an inflated balloon, on a piece of wool, and then you touch your neighbor's fancy hairdo, and it messes it all up because of static electricity. So the description of electrical potential like that is described using some of the math that Lagrange came up with. If you've had differential equations, you may remember so-called Laplace transforms. So think back to logarithms. People wanted to do big multiplication problems. Logarithms replace those by addition, which is easier. In differential equations, the equations have derivatives, calculus. Laplace transforms replace calculus with algebra. So you replace a differential equation with an algebraic equation, which is usually easier to solve. A brilliant idea. Maybe most importantly, Laplace was interested in probability and statistics. So for example, he founded the ideas that we today know as Bayesian statistics. He was instrumental in developing the central limit theorem, which is the idea that when we average a bunch of measurements, the results tend to follow a bell curve. And even the idea of randomness itself as a philosophical question he was interested in. Is it really random when we flip a coin? We call it so, but if we knew exactly which metal molecules were arranged in exactly which position, and we knew exactly which force we applied to exactly which part of the coin when we flipped it, shouldn't we be able to predict whether the coin would land heads or tails? Maybe, maybe not. And more importantly, we have a container of air, maybe the air in a basketball, and it's made up of these trillions and trillions of air molecules moving around and colliding with each other. If we were careful enough and had fancy enough equipment, could we really track each of those particles? Maybe, but we don't try. Instead, we talk about statistical averages of the motion of particles, which basically is what temperature is, by the way. And so maybe God could track it, maybe we could track it, I don't know, but is there anything really in the universe that is truly random? Fun fact, Laplace was fond of saying things like it's obvious that, or one can clearly see when he writes, and his readers quickly discovered what he really meant was, I know it's true, but it'd be tedious or clumsy or time-consuming to prove, and I don't really want to do it. things that he said were obvious really were not at all obvious. But Laplace's main interest was actually in celestial mechanics, astronomy, basically, but describing how things move. So, motion of the planets and comets in particular. Newton had done this very successfully, and he invented calculus to help him do it. But when he actually went to write his Principia textbook, instead of giving calculus-based proofs, he gave geometry-based proofs that were really hard to understand. So the Principia is a hard book to read, and it's not really how he thought about things and discovered such things to begin with. So Laplace went back and gave calculus-based proofs of all of these results. And that survives to this day. If you take university physics, calculus is just all over the place in mechanics, which it should be. Another thing, here's a quote from Newton. He says, talking about the solar system, this most beautiful system of sun, planets, and comets could only proceed from the counsel and dominion of an intelligent being. This being governs all things. So not only did God create the universe, but he's governing or controlling or making it work. The idea that somebody is involved in the universe and keeping things from falling apart. Now, during this time period, especially in France, this belief, religious belief, philosophical belief called deism is coming around. Deists believe in a creator, but that he no longer directly intervenes in the universe. And so the thing to keep in mind is a clockmaker. He makes a clock, he winds it off, and then he goes wandering off, and the clock goes tick-tick by itself. Laplace was a deist. And so, unlike Newton, who wrote things about God all over his physics textbook, Laplace did not. So Laplace and Napoleon Bonaparte were friends, and Napoleon, after glancing through Laplace's book, says, "You didn't include God in your book." And Laplace says, "I didn't need that hypothesis." Okay, we need to stop and think about what's going on here. In mathematics, we like to exclude hypotheses that we don't need. There's no point in assuming more than what you need to assume to prove a theorem. But now Laplace is saying, we can get God out of the picture. Our mathematics explains how the universe works. So God is not needed. God is not involved in our lives directly. And maybe God doesn't even exist. We really don't know. That's a big step from the time of Galileo or before up until about now. Most European mathematicians, like most Europeans, at least claim to be Christian. And now we're starting to see educated people question whether God is really necessary to explain math and science. Finally, let's say a few things about measurement standardization. So for historical reasons, people had been developing units of, say, length for centuries, thousands of years actually, and nobody was in charge of this. And so we had all sorts of weird measurements that didn't work together very well. So a poppy seed is a third or a fourth of a barley corn, depending on what time and place you're talking about. A barley corn is a third of an inch, so an inch is 3 barley corns, but then there's digits and fingers and so on. It's a mess. And so people were having trouble communicating their scientific results. The French Academy of Sciences in the late 1700s said, we gotta fix this. And so they appointed a committee to study how to standardize units of measurement. One of their big jobs was to decide, well, what are the elementary units or base units? Because these things are all hooked together by laws of physics. In this equation, the so-called pendulum equation, G is the Earth's gravitational constant, L is the length of the pendulum arm, and T is the period or the time that it takes to go tick-tock. And so you can't just think about L without length, without thinking about time, and vice versa. So they had a big job to decide where are we going to start before we define other things in terms of those starting units. They worked successfully. In 1799, France, adopted their recommendations, at least in part, and we now know it as the metric system. The two big things were the fact that all ratios were decimal based, so not 1/3 and 1/5 and so on. Everything's a power of 10. And also that, as we mentioned, that it was built from international standards, in particular, mass, length, and time. So for many years, for example, what we know as 1 meter was defined to be the length of this platinum bar that's in Paris, France. Since then, for various reasons, the physical prototypes like this have been mostly replaced by definitions based on natural constants. So today, for example, we define a meter to be the distance traveled by light in a vacuum in this tiny, tiny fraction of a second. That's better because it can be repeated in a science lab in any place in the world. You don't have to go and check the bar. We will stop there.